Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 37, Comets. Now that we've looked at the planets in our solar system, let's look at some of the smaller bodies that are in our solar system, and we'll take a look at comets. Before we get into the details of comets and where they come from and their characteristics, I do want to mention that you may have an everyday or maybe a couple times a year experience with comets, and those are meteor showers. If you've ever been outside at night to observe a meteor shower, you have seen pieces of a comet burning up in the Earth's atmosphere. So first of all, let's talk about what shooting stars are. If you go out at night and you see a shooting star, the first thing to know is it has nothing at all to do with stars. Shooting stars, it's a terrible name. They don't come from stars. They're actually little tiny pieces of rock or ice that are burning up in the Earth's atmosphere. Now, there are sporadic meteors, which if you go out on a dark night, you should see a meteor about once every 5 to 10 minutes if the skies are really dark. If there's a lot of light pollution, you'll see far fewer meteors, but under dark skies, you'll see one about every 5 or 10 minutes or so. But a couple times a year, there is a strong meteor shower. There are many weaker meteor showers, and I don't recommend that you go out to see those. I'll talk more about that later on. But every now and then, there is a strong meteor shower. And when there's a strong meteor shower, on a really good one, you might see 1 meteor per minute or so. These are particles that came from comets. Now, what happens as a comet orbits the sun? We're going to find out that a comet is a dirty snowball. It is primarily made of ice, water ice, methane ice, ammonia ice, frozen carbon dioxide, frozen carbon monoxide. It's made of lots of different ices, but primarily water ice. And as a comet comes close to the sun in its orbit around the sun, the comet warms up, some of that ice sublimates, goes from a solid to a gas, and it also releases little chunks of ice and little chunks of rock and dust. Now, those little chunks of rock and dust, well, they continue in the same orbit that the comet had before. And if it so happens that the comet's orbit intersects the orbit of the Earth, as we orbit the sun, when we pass through that cloud of debris, we get a meteor shower. And a meteor shower is typically they last for a few hours. They might even last for a few days for some of the stronger showers. What we're seeing are little particles from the comet, and the Earth is plowing through this stream of material. And as the Earth plows through the stream of material, we see little tiny chunks of ice and rock burning up in our atmosphere, and we get a beautiful meteor shower. This is the Geminid meteor shower. It's a wintertime shower that's visible in December. And this is a long exposure, so you don't see that many all at once. You typically see about 1 per minute. But you'll notice they all seem to be coming from one part of the sky. In this case here, all the meteors seem to be originating out of one part of the sky. That is a trick of perspective. And that trick of perspective, you're probably familiar with it if you're driving in an automobile and it's raining outside. If you look towards ahead of you, you will see that all the raindrops appear to come from one spot ahead of you. And that is the spot that you are driving towards. As you drive towards that spot, it looks like the raindrops are coming away from it. The same is true with meteor showers. There is a point that they seem to originate from, and we call that point the radiant. And the constellation where the radiant is what gives the meteor shower its name. So the Perseid meteor shower in August, the radiant is in the constellation of Perseus. The Geminid meteor shower in December, the radiant of that is in the constellation of Gemini, the twins. So all the meteors seem to streak out of the radiant. And as I said, it's just a trick of perspective right there. When you see a meteor streaking through the sky, you're seeing something that is somewhat bigger than a grain of dust burning up in the atmosphere. A typical bright meteor from the Perseid meteor shower might be the size of a little small piece of granola, for example. So imagine when you're eating your cereal, you have a couple small pieces of granola. That's the size of the meteors as they're burning up in our atmosphere, the little tiny chunks of ice and or rock. Now, I think the two best meteor showers every year are the Perseids in August and the Geminids in December. And to see the Perseids, what you want to do is go out about 11 o'clock in the evening. You want to look towards the northeast, and then you want to be out for at least a couple hours. And in August, I'll show you the dates here in a minute, but typically it's around August 12th to the 13th of every year. You look in the northeast. You don't want to look right at Perseus because that's where the meteors are coming straight at you. You want to look high in the sky, but near the radiant in the sky, and you will see meteors streaking away from that point. And in a good year for the Perseids, if you're under dark skies away from light pollution, you'll see about 1 meteor per minute. But here's the thing. You have to go out late at night. Meteor showers are always better after midnight, and they really never start until about 10 or 11 in the evening. And the reason for this is think about our orbit around the sun. Here's the north pole of the Earth. Here is the Earth. Remember, the Earth turns counterclockwise as seen from above. Here's an observer on the Earth, and you've done this many times. This is noon, sunset, midnight, and sunrise. Well, the Earth is orbiting around the sun at 30 kilometers per second, which is 18 miles per second. And since we're moving so fast in this direction, we will meet more meteoroids head on than will catch up with us from behind. The analogy that I like to use, it's like your windshield, right? When you are driving down the highway, all the bugs get splattered on the front windshield. Hardly any of them ever catch up with you and splatter on the rear windshield, right? All the bugs end up splattered on the front windshield. Well, the front windshield is between midnight and sunrise. Between midnight and sunrise, you are on that part of the Earth that is facing in the direction that the Earth is going, and so you're going to see far more meteors at that time of night. Between sunset and midnight, the meteors have to be catching up to us in order for you to be able to see them, and there just aren't many meteors that are doing that. Of course, there are many meteors during the daytime, but we can't see them because the sun is up in the sky. But there are ways you can detect meteors like that using radio waves, but we're not going to talk about that now. These are some of the prominent, reliable meteor showers every year. But I have to say, I think really the two to go out and watch are the Perseids in August and the Geminids in December of every year. And that's because they're two of the strongest showers. These are the number of meteors you can expect to see per hour. So for the Perseids, you'll see about 40 per hour. For the Geminids, you'll see about 50 per hour. These are the comets that they are associated with. The Perseids come from a comet called Swift-Tuttle, and the Geminids actually come not from a comet at all, but from an asteroid, in fact. So the Geminids are actually material that comes off at least what appears to be an asteroid today. It may, in fact, be the dead nucleus of a comet. But notice most of the other meteor showers are not nearly as strong. And I've noticed in recent years that the media tend to make a big deal about some of these not so very strong meteor showers. This year, for example, the media said a lot about the Lyriad meteor shower in late April. And I have to tell you, the meteor rate here is going to be 8 per hour. And you're probably not, if you have any light pollution at all, you're probably going to see less than half that. And so that's a meteor once every 15 or 20 minutes, and that's just not that impressive. I think if you're going to go out and see a meteor shower, the two to go see are the Perseids and the Geminids, and ignore all the others. And then once you've seen the Perseids a couple times and seen the Geminids a couple times, then you can go out and look for some of the fainter meteor showers, but don't let the Leonids or the Lyriads be your first major meteor shower, because I think you'll walk away disappointed. Of the two showers, the Perseids or the Geminids, my favorite one is the Perseids, and it's for no other reason than because they occur in August. It's a really nice time of the year to lay out at night watching the sky. The problem with the Geminids is they occur in December, typically around December 12th or 13th of every year, sometimes the 14th, and it's pretty cold that time of the year. It's pretty tough to lay out at night. But thanks to these meteor showers, thanks to stuff that the Earth is sweeping up as it orbits around the sun, the Earth gathers up 1 to 2 tons of debris every hour. The Earth is growing larger and larger every hour by 1 to 2 tons. But given the massive size of the Earth over the lifetime of the Earth, this will not add appreciably to the mass of our planet. It did add appreciably early in the solar system when lots of things were crashing to the Earth and the Earth was building up. But today, accretion of these things does not add much to the mass of our planet. Every now and then, the Earth will pass through this this trail of debris. So every now and then, one of these comets will come through the solar system, and just after it passes, the Earth might happen to pass through that tail of material right after the nucleus, right after the comet's gone through. And in that case, the Earth will be passing through a particularly dense meteor shower, a particularly dense part of the stream, and you will get not what's called a meteor shower, but a meteor storm. And the most famous shower that's associated with meteor storms is the Leonid meteor shower. The Leonid meteor shower has been responsible for some of the most spectacular meteor showers in all of human history. Probably the most famous of these was in 1833. In 1833, hundreds of thousands of meteors were seen to fall in the course of a few hours in the middle of the night. It was such a dramatic display of meteors that people were woken out of their bed to get ready for the end of the world, that Judgment Day was at hand. In fact, one of my favorite stories about this meteor shower is that Abraham Lincoln was a young man, and he was sleeping soundly when the homeowner, the person that he was lodging with, woke him up and said, "Abraham, arise, it's time to pray. Judgment Day is at hand." And Lincoln went to his window and he looked outside and he saw thousands of meteors streaking through the sky. But he also saw behind them the stars in their fixed places, not moving. And he said, the world did not end then, nor would the Union now. He used that as an example during the Civil War to say that the United States would not end as part of the Civil War, just as the world did not end in the 1833 Leonid meteor shower. The Leonids are responsible for a storm of meteors about every 33 years. They happened in 1833. There was a good storm in 1866. Astronomers predicted that there would be a storm in 1899, and in particular, an astronomer here at the University of Virginia by the name of Charles Olivier, predicted a storm in 1899, and it didn't happen. People went outside expecting to see this amazing display of meteors, and they did not see it. And Olivier said that it was one of the greatest disappointments in the public's eye for astronomy. The next year, there was a fairly strong shower. There wasn't much in 1933, but then in 1966, there was another amazing Leonid meteor storm when tens of thousands of meteors were seen over the course of a few hours. There was also a Leonid storm in 1999 and 2000, and the next one is coming up in 2033. Now that we can measure the orbit of the comet very precisely, we can predict what the storms will be like. And I'm afraid to say that it seems like the best of the Leonid meteor storms are over for right now, that the one in 2033 and the one in 2066 will not be spectacular meteor storms, but you should still be on the watch out for them and make plans to see them because they only come around once every 33 years. It may not storm that night so that you see thousands of meteors, but I will say in 2000, here at the University of Virginia, we held a viewing event with students. We went out to some of the athletic fields on North Grounds, laid out in the middle of November on a bitterly cold night, and I saw about 500 meteors in the course of just a few hours, and that was by far the best meteor shower I've ever seen. So let's talk a little bit more about comets. What are comets? In summary, comets are essentially dirty snowballs. They are primarily, as I said earlier, made of ice, but mixed into that ice are lots of little chunks of rock and dust. As the comet approaches close to the sun, the heat from the sun warms up the ice sublimates, that is, it goes from a solid to a gas, and it releases lots of little tiny particles of ice and dust. Now the sunlight, the solar wind, the wind from our sun, impinges on these particles and it blows them backwards in a beautiful tail. So it's always important to know that the tail of a comet always points away from the sun. And this was realized even in ancient times. Even in ancient times, they realized that the sun had something to do with comets because the tails of comets always pointed away from the sun. We recognize today that most comets consist of two tails. There is a blue tail called the ion tail and a yellow tail called the dust tail. The dust tail are those little tiny chunks of ice and rock and dust, and they get left behind in the orbit that the comet is taking around the sun. And then there is the ion tail. This is made of individual atoms and molecules. Atoms and molecules are very, very small. They're so small and so lightweight that the solar wind blows them directly away from the sun. So the ion tail, the bluish ion tail, always points away from the sun. The dust tail usually points in the direction that the comet has come from, usually follows the orbit of the comet. Now, many of our comets come from the Oort cloud. The Oort cloud is that giant cloud of comets that may stretch as much as a light year or two from our sun. There are probably billions of cold, icy bodies out there in the Oort cloud, and every now and then a star will pass too close to our solar system or pass close to our solar system, and its gravity will disturb the orbits of these objects, and they will end up plunging into our inner solar system. And when they plunge into the inner solar system, they end up on orbits that have periods of thousands or tens of thousands of years. That is, they will only visit the inner solar system once every thousands of years. But every now and then, one of them, as it comes to the inner solar system or on its way out of the solar system, will have a close encounter with the planet Jupiter, or one of the other planets, but usually Jupiter. The gravity from Jupiter is strong enough that it can change the orbit of the comet. So now, instead of taking thousands of years to orbit the sun, it can take just hundreds. And over time, other encounters with the planets can shorten that period until you end up with a comet like Halley's Comet, which takes 76 years to go around the sun. We see Halley's Comet once every 76 years. Now, the main parts of a comet are shown here. So the nucleus of the comet is the actual dirty snowball itself. And typically the nucleus of a comet is about 6 miles across, or about 10 kilometers in diameter. And that's tiny. It's especially tiny compared to what we see. It's hard to believe, but the nucleus itself that's causing all of this is actually just a tiny, tiny little speck located down here at the very head of the comet. That is the nucleus of the comet. Surrounding the nucleus is the coma, and the coma is material that has recently come off of the comet. It is the stuff that the comet has shed. And then the solar wind will blow that material away, and we will get the ion tail that points directly away from the sun. So you can see here's the sun, there's the ion tail, and here is the comet's motion, and you can see the dust tail, that yellowish colored dust tail that's made up of little tiny particles of dust and rock and ice. Is curved coming out from behind the comet there. It's a combination of the sun blowing it away and those particles remaining in the same orbit that the comet had. And you can see here that the coma of the comet can be 1 million kilometers across. So when we look at these comets like this, let's use this one right here, Hale-Bopp, which was visible in 1996. By the way, a spectacular comet in 1996. The coma here is about 1 million miles across, and the nucleus is just a couple kilometers wide down there at the center. All right, we have sent a number of spacecraft to examine comets up close. And so what I'm going to show you now are just talk a little bit about that. In 1986, Halley's Comet returned to the inner solar system for the first time since 1910. A number of nations decided to send spacecraft to Halley's Comet. Unfortunately, the United States was not one of those. NASA asked Congress for the funding to send a mission to visit Halley's Comet, and they were denied. But the European Space Agency, Japan, and Russia sent multiple probes to examine Halley's Comet. And the most ambitious of these was the European Space Agency's mission, where they passed close enough to the nucleus of the comet to get very good, excellent images at the time of the nucleus of Halley's Comet. And two surprises came out. The first one was the shape. People had expected Halley's Comet to be roughly round in shape. It's made of ice, which doesn't have a lot of structural integrity, so the guess was that gravity would have pulled it into a roughly round shape. Instead, we found something shaped like a giant potato, a really distorted potato. The most surprising thing of all was the color. It was expected to find something made primarily of ice, which we would expect to be light-colored, almost white. In fact, instead, we found an almost jet black object. Halley's Comet, and it turns out all comets, are covered in little chunks of rock and dust that are very dark, almost black in color, and are very, very rich in organic materials. It is comets like this crashing to Earth that probably not only seeded our oceans, but seeded our oceans with the organic materials that were necessary to to arise life here on our planet. Now, since the visit to Halley's Comet in 1986, we have made many other trips to comets. A couple of the more famous missions are the Deep Impact mission to visit Comet Tempel 1. So this is a close-up image of Comet Tempel 1. What was amazing about the Deep Impact mission was it carried a second separate spacecraft, and the job for that second separate spacecraft was to collide with the comet, to literally blow fresh material off the surface of the comet. And as it blew that fresh material off the surface of the comet, the main spacecraft would actually fly through that material and sense what that material was made of. At the same time, observers on Earth could observe the comet and look, using spectroscopy, look for the signature elements that were there to determine what's there. So that was Comet Tempel 1. That was the mission Deep Impact, a tremendous success. The impactor, as you can see in this image, actually struck the comet. And we were able to blow material off the surface and determine what the comet was made of. Surprisingly, up until this point, astronomers had described comets as dirty snowballs. That is, they're primarily made of ice with a little bit of rock and dust mixed in. Comet Tempel 1 taught us that some comets, maybe many comets, are actually icy dirt balls. That is, they're primarily made of rock and dust with a lot of ice mixed in, but they are predominantly rock and dust. Okay, and that collision, by the way, with Comet Tempel 1 was in 2005. Now, scientists have been studying, and people have been studying comets for thousands of years. Here is an image from the famous Bayeux Tapestry that shows you Halley's Comet in the year 1066. Halley's Comet was seen in the year 1066, and it was seen as a bad omen for King Harold II, William of Normandy. It foretold the defeat of Harold II by William of Normandy in 1066. Now, we have visited over the years a number of asteroids and a number of comets. So here is to the same size scale. These are some of the asteroids that we have visited in the asteroid belt. These are some of the comets that we have visited. Here's Halley's Comet that was visited by the European Space Agency's Giotto spacecraft. We visited Comet Borrelly, Comet Tempel 1 with the Deep Impact mission. With the Stardust mission, we actually visited Comet Wild 2 in 2004, and Deep Impact and another mission visited another comet called Hartley 2. And for visiting asteroids, a number of spacecraft over the years have visited a number of different asteroids. By far the best and most ambitious mission to visit a comet is the European Space Agency's Rosetta mission. Rosetta was launched in 2004 on a 10-year journey to get to the comet 67P Churyumov-Gerasimenko. I'm just going to call it Comet 67P because I have a hard time getting out the name Churyumov-Gerasimenko. But Comet 67P is a comet that orbits in the inner solar system. And the goal for Rosetta was to not only visit the comet, but to orbit it and study it for many, many months as the comet came into the sun, and we could see the comet go from being dormant to getting active. It not only studied the comet, but it brought along a little lander called Philae, and Philae landed on the surface of the comet on November 12th in 2014. It actually bounced twice on the surface. We'll talk more about that in a minute. But here's the Rosetta spacecraft. It was a very capable spacecraft. And then here it is with its little Philae lander that landed down on the surface of the comet. Here is the journey that Rosetta had to take to get from Earth out to the comet. The comet orbits in a very elliptical orbit, so you can see the very elliptical orbit of 67P right here. So after launch, there was one encounter with the Earth. There was an encounter with Mars. There was yet another gravity assist here you will see with the Earth. And so those two Earth gravity assists and that Mars assist put the spacecraft on an asteroid, on a more elliptical orbit. It visited an asteroid in the asteroid belt, had another third Earth assist, and this one put it on an orbit that more closely matched the orbit of the comet. So here's the comet out here, passed by another asteroid in 2010. And this is the orbit of Jupiter out here. So you can see this comet goes out beyond the orbit of Jupiter, falls to the inner solar system. So the spacecraft was put in deep hibernation in 2014. It met up with the comet. It made a major maneuver and it matched orbits with the comet, and it was going to follow the comet for the next few months, or actually I should say next few years, as the comet fell to the inner solar system and became very, very active. So that was the orbit. So what did Rosetta find when it went to the comet? Here's an artist's depiction of what they expected to find ahead of time, and here is what they actually found. The comet 67P is either a contact binary, two bodies that actually join together at some point in the solar system, or a large body that has oddly eroded to produce this neck right here. But 67P is an amazing object. It is a mostly icy body with lots of rock and dust mixed into it, but it is what a comet looks like. To give you an idea of how big this thing is, there it is compared to a major metropolitan city. So if we were to take this thing and put it on the surface of the Earth, of course, it's not held together near enough. If we did this and put it on the surface of the Earth, it would immediately fall apart because it's barely held together by its own gravity. The ice and the rock and the dust are not tightly bound to one another. But in any case, that's what it would look like next to a major city there. As the comet came to the sun, the spacecraft was able to see it getting active. It was able to see jets of material shooting off the surface as the ice sublimated and melted and brought with it little tiny particles of rock and ice. Here are more pictures of the spacecraft before launch. It was solar powered with its giant solar arrays right there. I love this photograph taken by one of the navigation engineering cameras on board. The camera was designed to look at the solar array right here, but it happened to catch the comet in the bottom part of the photograph. Rosetta came within a few tens of kilometers of the surface and just returned some absolutely spectacular images of the surface of the comet right there. We see smooth patches that are covered in lots and lots of dust. We see rough areas. We see lots and lots of boulders sitting on the surface. Of course, these boulders are probably not solid rock, but mostly made of ice. We see cliff faces, smooth areas, regions where the jet material is coming out of the comet. Just really spectacular images taken by Rosetta. Scientists will be studying these images for years to come to learn more about how this comet was held together and put together. Well, after many months of studying the comet, scientists decided that they were going to land the Philae lander on the edge of the comet up here on one of the ends of one of the lobes of the comet. That was the designated landing site. The lander was battery powered, so it would only last for a couple days. It did have some solar arrays on it, but they weren't enough to continually charge the battery. That is, the lander couldn't keep running continuously. It was going to run for a couple days, and that was the landing site that was selected so that it could land on the surface. It had a small robotic arm that would be allowed to probe the surface. It had other instruments that would tell us what the surface of the comet was made of. And on the given day in November 2014, the probe was released. This is an actual image of the Philae lander departing from the Rosetta spacecraft as gravity dropped it down to the surface. There is one of the pictures that was taken by the Philae lander as it came close to Rosetta. As it fell towards the comet, the orbiter was able to take pictures of it. So here it is falling. There it is continuing to fall. And then that is where it touched down on the surface of the comet. And we know that it touched down there because there's a before image and an after image, and you can actually see the footprints where it touched down. But here's where the problems began. Philae had a couple different ways to try and hold itself to the surface of the comet. Remember, the gravity of a comet is incredibly weak. It is so weak that standing on the surface of the comet, it is not hard at all to escape from the surface. So, if Philae bounced off the surface, it could actually escape from the surface of the comet. So to make sure that it didn't bounce and escape, it had a system where it would shoot a harpoon into the surface and reel itself down. There were other things. There were a series of jets that would fire as well to try and hold it down on the surface. Unfortunately, these failed. The harpoon failed, and Philae bounced on the surface. What that meant, after it bounced, it was last seen over here, that little white dot right there. There is the Philae lander. It ended up in some unknown location. Here's a photograph, an up-close photograph. In fact, I think it's the last photograph that was taken of the landing site before Philae bounced. Eventually it bounced and it came to rest, and it took many, many months before scientists were finally able to locate where Philae came to rest. It came to rest at the base of a giant cliff, and this is one of the photographs that the cameras returned. Of the face of that cliff. So we are looking at things here very, very up close. These are instruments on the end of the Philae lander. So we are looking at things here, little chunks of rock and ice that are just a couple inches across. Here's a schematic with the different cameras and the pictures that they took and how the spacecraft was oriented. It turns out it came to rest on its side. So one of the cameras was actually looking out into space, and the other cameras were one was looking at the cliff face and the others were looking at the comet underneath the spacecraft. The Philae lander was never able to accomplish all of its scientific goals because of its bounce and the fact that it ended up landing on its side. We never got quite the information from it that we wanted to get. Nevertheless, the Rosetta mission was an outstanding success, spending many years in orbit around one of these comets. Over the next few years, as the data from Rosetta is still analyzed, we're going to learn a tremendous amount about comets. Hopefully, in your lifetime, there will be at least a few bright comets that you can see with the naked eye. Certainly, you should look forward to seeing Halley's Comet in 2061. Make plans to see Halley's Comet when it returns to the inner solar system in 2061, but hopefully before then you will see another bright comet. Every few years, bright comets are visible in our night sky, many of them coming from deep out in the solar system. And we can't predict when they will show up. Typically, they are found by an amateur astronomer who is scanning the sky looking for them. In honor of their discovery, the comet is named after the astronomer. So Comet West was named after a person. Comet Hale-Bopp was named after the two discoverers, Alan Hale and I can't remember what Bopp's first name was, but two astronomers who discovered the comet. But hopefully you'll get to see a couple naked eye comets in your lifetime. Look at them with binoculars. If you have a telescope, go out and see them because they really are amazing things to see. So that is comets. Thank you very much, and I will see you later.